Hi viewers, welcome to my class on mechanics of materials. In today's class, we'll work out another example for shear force and bending moment diagram for an overhanging beam subjected to a uniformly varying load, coupled and a point load. Let us work out. Draw the shear force and bending moment diagram for the beam shown in figure. So this beam is supported at B and F and it's subjected to a point load 30 kN at A and a UVL with intensity 0 at one end and 50 kN per meter at the other end. So it's a triangular load acting over 6 meter length and an anti-clockwise coupled 40 kN at E. As a first step, let us find out the support reactions. Now to find out the support reactions, we have to take the moment summation with respect to point B. Now you cannot take with respect to point A, since if you take moment summation with respect to point A, both the reactions will come into the equation. So while taking the moment center, you have to choose one of the supports. So taking the moment summation with respect to point B, we will get the moment of this 30 kN as minus 30 into 2. This is producing an anti-clockwise moment with respect to B. So minus 30 into 2, and UVL you have to replace by a point load. Resultant load due to UVL you can calculate as the area of the triangle. So 50 into 6 by 2. 50 is the intensity multiplied by span divided by 2. That will give the area of this triangle, half base into height. So that is half of 6 into 50. So 50 into 6 by 2, that will give the area, and it is 150 kN. So the resultant load is 150 kN, and the resultant load, when you replace it by a resultant load, you have to replace at a distance of 2/3 of span. Span is 6 meter, 2/3 of 6 from the zero intensity side. So 2/3 of 6 is 4 meter. From here, a higher intensity side, if you take 1/3, that is 1/3 of 6 is 2 meter. So from C it is acting at a distance of 4 meter, or from B it is acting at a distance of 5 meter. So the moment of this UVL is 150 into 5 meter, 4 plus 1, 5 meter. So 50 into 6 by 2 into 5, that is the moment of this triangular load. Again this couple is acting, so minus 40, the couple moment of the couple is minus 40 since it is anti-clockwise. Then this reaction RF will produce a counterclockwise moment, and the distance of that support is totally 10 meter. So minus RF into 10 is equal to 0. So you can find out RF as 65 kN. So after getting the reaction at the support F, that is RF, you can find out RB as the total downward load minus RF. Now total downward load is 30 plus 150, so that is 180. Downward load is 180. 180 minus this 65, or you can sum up the forces in the y direction, minus 30 plus RB minus 150 plus RF, that is 65, is equal to 0, or RB is equal to 180 minus 65, which will give 115 kN. So you got the reaction at B and reaction at F. So we got the reaction at both the supports. Now let us calculate the shear force at various points. Now first section, shear force is going to be constant because in between A and B there is no load acting. So shear force for this section AB is constant, and when you take a section here, left side only one force is there, and that is acting downward. So minus 30 is the shear force for the section AB. So shear force for the section AB is minus 30. Similarly, between B and C also there is no load acting. So between B and C, shear force is going to be constant. And when you take a section, there are two loads, minus 30 and this upward load plus 115. So shear force in this section is minus 30 plus 115. So that will give 85 kilonewton for this section. So for BC also the shear force is constant and its value is 85 kilonewton. Whereas this part the shear force is negative minus 30 and here it is positive 85 kilonewton. Now due to UVL, shear force will continuously decrease, but the decrease is going to be a parabolic variation. Now for UVL also you have to calculate shear force at either ends. So here you have to calculate immediately right of C and immediately left of D. When you take immediately right of C, the part of UVL added is negligibly small and there is no point load acting here. So shear force for the section BC and immediately right of C will remain same. So immediately right of C, you can only see two forces, minus 30 and plus 115, and this part of load you can neglect because you are only taking a section immediately right of C. So immediately right of C you have shear force 85 kilonewton. So there is no change here at point C. Also at left of D you should calculate immediately left of D. When you take, the complete UVL will come, and this is not a point load, this is only intensity we have marked. So immediately left of D, this part of load is going to be negligibly small and the complete UVL will come here. So this complete UVL means it's minus 150. So whatever value you had here for shear force, minus 150, that will give the shear force immediately left of D. So shear force immediately left of D is minus 30 plus 115 minus 150, this resultant of UVL. That will give minus 65 kilonewton. Now for the section DE, from D to E there is no force acting, and even for the section EF there is no load. The couple you can neglect while drawing the shear force diagram, while calculating the shear force. So for DE and EF there is no further load added here. So from left of D, when you move to the right of D also, there is no load part added. It's not a point load, so only intensity is given. So this part is of load is negligibly small. So when you move from left of D to DE, there is no extra load added. So for the section DE also, the shear force is minus 30 plus 115 minus 150. So for section DE you have minus 65. Even for section EF the same shear force is acting. So there is no addition of load. So section DE and section EF all same shear force is acting, minus 65 kilonewton. So this part of the beam you will have a negative shear force, minus 65. Only under UVL you will get a parabolic variation, and parabolic variation with a greater slope at the end, because major intensity is concentrated here, so it will decrease suddenly at the end but gradual at the beginning, and you will get a concave side down for this variation. Now let us calculate the bending moment at various points. Now bending moment at A, you know, it's going to be 0, and even at F bending moment is 0. Now you have to calculate the bending moment at B. Bending moment at B is minus 30 into 2. So this force is producing a negative moment. So minus 30 into 2. Minus 30 into 2 or minus 60 kilonewton meter. That is bending moment at B. Now bending moment at C you can calculate as minus 30 into 3 plus this reaction 115 into 1. So minus 30 into 3 counterclockwise bending moment, and for this force is producing a positive bending moment. So 115 into 1. So that will give 25 kilonewton as the bending moment at C. Next you have to calculate the bending moment at D. Bending moment at D is minus 30 into total distance is 9. Minus 30 into 9 plus 115 into 7 meter. So total this distance is 7 meter. So plus 115 into 7. And this load when you take at D, this complete load 150 kilonewton, that is a resultant of UVL 150 kilonewton, which will act 4 meter from here, but from the D it is acting 2 meter away. So this load will produce a negative moment. So minus 150 into 2 meter. Since we are calculating bending moment at D, this minus 150 into 2 distance you should take. So bending moment at D is minus 30 into 9 plus 115 into 7 minus 150 into the distance is 2 meter. So that will give 235 kilonewton meter. That is the bending moment at D. Next you have to calculate the bending moment left of E. Left of E, wherever couple is acting, immediately left and right side you should take. So immediately left of E, without considering this couple, you should calculate the bending moment. So when you move from section D to left of E, increase in distance is 1 meter. So all these forces are there, all the three forces, same forces are there. All these forces will produce bending moment, and same three forces, that is 30 kilonewton, 150 kilonewton and this 150 kilonewton. All these forces were there at D. Now when you move to left of E, there is an increase of distance 1 meter. So you have to only increase the distance by 1 meter, that is 9 will increase to 10, that is minus 30 into, instead of 9 you have to increase by 1 meter, that is 10, and again 115 into, instead of 7 you have to increase by another 1 meter, 8 meter, and for this 150 kilonewton it was 2 when you calculated bending moment at D. Now you have to increase to 3, another 1 meter you should add. So minus 150 into 3, that will give the bending moment immediately left of E. If any other load is there, that you should add between D and E, between previous section and next section. If any other load is there, you have to include the bending moment of that load. Okay, so bending moment left of E is minus 30 into 10, instead of 9 you have 10, and plus 115 into 8 meter, instead of 7 you have 8, and 150 minus 150 into 2 plus 1 3, so we have increased it by 1, so which will give 170 kilonewton meter as the bending moment left of E. Next, immediately right of E, from here when you move to the right of E, bending moment created by all these forces remain same. So you have to only add this couple. Here it is anti-clockwise, so you have to take 170 minus 40. You have to subtract this value, that is minus 40, from this previous section, that is left of E 170 minus 40, that will give bending moment at right of E, that is 130 kilonewton meter. Bending moment right of E is bending moment left of E minus 40, or 170 you add here, 170 minus 40, which will give the bending moment right of E, and bending moment at F is 0. That gives the bending moment at various marked points. Now let us draw the shear force diagram for the beam. Now we have seen that shear force for the first section is minus 30, and for the second section is plus 85, and for this UVL it is parabolically varying from 85, right of C 85 to left of D minus 65. So 85 to 65 is the variation in the section CD. 85 to minus 65. 85 to minus 65 is the variation in this section CD. So you have to show the parabolic variation from 85 to minus 65. But this parabolic variation you have to show with the concave side down. Concave side of this curve should be down. You should not plot in the opposite direction with the concave side up. As this part the slope will be less because only reduction in shear force is less here. So the slope will be gradually increasing, and at the end the slope will be maximum. So because larger part of the load is here. So this is how you have to plot the shear force variation for this UVL. Next, for the section DE and DF, you have minus 65 as the shear force. So you can draw that horizontal line and complete the shear force diagram. Here you have a reaction plus 65 that will close this shear force diagram. Now you can observe that under UVL the shear force is changing its sign. So this point you will have a peak for the bending moment curve. So we have calculated the bending moment at A, B, C, D, left of V, right of V and F. We did not calculate the bending moment corresponding to this point. We know the bending moment at C, we know the bending moment at D. But between C and D you are going to get a peak corresponding to the point where shear force is 0. So wherever shear force is 0 under UVL or UDL, there you are going to get a peak or bending moment curve, you are going to get a slope 0. Slope 0 means there will be a peak, and that peak point has to be marked, or this point has to be identified what distance this shear force is coming to 0, that you should find out, and then corresponding to this point you should calculate the bending moment. So to get this point you have to write down the shear force equation for this section. So shear force equation, this point is coming in the section CD. So you have to take a section here, calculate the shear force for that. Now, shear force means sum of all these forces left side of that section. But this section you don't know the location to get the exact value of this UVL. So let us do that. So I have taken a section at a distance x from the left end, and this x value goes from 3 to 9 meter. It can be anywhere between 3 and 9. 3 means at C and 9 means at D. So x value can vary from 3 to 9. So our intention is to find out the distance at which the shear force is coming to 0. So you have to write down the shear force equation for this section. So to calculate the shear force, we know these forces, but this part of load you should calculate. This part of load we don't know. It depends on x. If x is more, this part of load will increase. So this part of load, if you have to calculate, you should know the intensity here. For a triangle load, you calculate part of the load by area of this diagram. Area of this diagram. To calculate this area, you should know the intensity here. So intensity I marked it as H. So this intensity, if it is known, you can calculate this area. So calculation of this intensity varies linearly with respect to the distance. Okay, so the distance is from C. If I mark this distance is x minus 3, so total is x. Section is marked from at a distance x from the left end. So this distance is 3. So from C section is at a distance of x minus 3. So you can use a similar triangle method to calculate this h. H by 50, ratio of similar sides, h divided by 50. I am considering two triangles. One is this small triangle and the other one bigger triangle. So h divided by this intensity is 50 is equal to x minus 3 divided by 6. So ratio of similar sides, h divided by 50 is equal to x minus 3 divided by 6. So from that you get h as x minus 3 by 6 into 50. So that is the intensity at a distance x. Now if x is 3 meter, you should get intensity 0. Okay, x is 3 meter is here. So when x is 3 meter, you should get intensity 0. X is 3 meter, you are getting that intensity 0. Now x is 9 meter, that is at D, you should get intensity as 50. So let us substitute and see. X is 9, you are getting 9 minus 3, 6 by 6, you will get 1 into 50. So you are getting 50 kilonewton per meter. So this equation will give the intensity of the load at any distance between 3 and 9, that is under this UVA. So we got the expression for the intensity, we got the expression to calculate the intensity at any location in this triangular load. Now after getting the intensity, you can calculate this part of load as area of this triangle. So how do you calculate the area of this triangle? As half of base into height. That is, the intensity is h, base is x minus 3. So base into height divided by 2. So base is x minus 3, height is x minus 3 by 6 into 50 divided by 2. So it's bh by 2 I have used. So that will give 50 by 2, 25 divided by 6, give x minus 3 square. So 25 by 6 into x minus 3 square, that will give the part of UVL, that is resultant of this UVL part. So that will act downward. So that load is acting downward. So when you take a section, there are 3 loads, minus 30, plus 115, and this part of load which is minus 25 by 6 into x minus 3 square. That is going to be the shear force equation for this section. So let us write down that. So shear force for the section CD is, in the section CD, anywhere you can use this equation. So shear force equation for the section CD is minus 30 plus 115 minus 25 by 6 into x minus 3 square. This load, I have shown here the load, minus 25 by 6 into x minus 3 square. This is the shear force for the section CD. Now we have to find out at what location this shear force is coming to 0. You can use this equation to find out the shear force at any point between C and D. But we have written this to calculate the point where shear force is coming to 0. So you can equate this equation to 0. So this is minus 30 plus 115 is 85, minus 25 by 6 into x minus 3 square. So x minus 3 square I have expanded, x square minus 6x plus 9. So that is the shear force for the section CD. I equated this to 0 and reduced this equation. You get x square minus 6x minus 11.4 is equal to 0. Now solving this, you get two values of x. X is 7.517 meter and another minus value, minus 1.517 meter. Minus value is not relevant here, so you can select 7.517, which is lying in the section CD. So this is the solution, and this point at a distance of 7.517 meter, the shear force is coming to 0. So corresponding to this point, at this location, you should calculate the bending moment. So let us calculate the bending moment corresponding to that point. The same section, I am calculating the bending moment. Okay. The forces we know, you have to only multiply with the distances. So the force is 30, minus 30 at a distance of x. At this section you are calculating the bending moment. So minus 30 into x, okay, plus 115 into this distance. This distance is going to be x minus 2, 115 into x minus 2. it's producing a clockwise moment. So 115 into total is x, subtract 2, which will give the distance from the section considered. So 115 into x minus 2. And this load, we already know the part of the load as 25 by 6 into x minus 3 square. Now this is acting at a distance of, base is x minus 3, total is x, you have subtracted 3 meter, so which gives x minus 3. So the span over which this part of the load acts is x minus 3. So the resultant load will act at a distance of x minus 3 by 3. And this is going to be 2/3 of x minus 3, but this is 1/3 of x minus 3, that is x minus 3 by 3. So the distance is x minus 3 by 3, 1/3 from the higher intensity side, 1/3 of span from the higher intensity side. So 1/3 of x minus 3. The load is known, 25 by 6 into x minus 3 square into the distance is x minus 3 by 3. So that is producing a negative moment, so minus. So this will give the bending moment equation for that section. So I have reduced this, minus 30x plus 115 into x minus 2 minus 25 by 18, 6 into 3, 18 minus x minus 3 cube. So this will give the bending moment equation. Now in this equation you have to substitute x as 7.517. At this location you should calculate the bending moment. Substitute x as 7.517 meter. So substituting x as 7.517, you will get minus 30 into 7.517 plus 115 into 7.517 minus 2 minus 25 by 18 into 7.517 minus 3 cube. So that will work out to 280.943 kilonewton meter. So this is the peak bending moment in that section. So we have calculated at C and we have calculated at D, and between C and D there is a peak and the value is 280.943 kilonewton meter. Now we have to mark this value while drawing the bending moment diagram. Now let us plot the bending moment diagram now. So we already plotted the shear force diagram, and this is the point where the peak is coming. So let us plot from left side. At A bending moment is 0, at B bending moment is minus 60, and you know the variation is linear variation because shear force is constant for that section. So bending moment variation is linear from 0 to minus 60. Next at C we have bending moment as plus 25. So plus 25 bending moment at C. So bending moment at C is plus 25. So minus 60 to plus 25. So you can draw a straight line because shear force is constant. So the variation is linear. So you can join by a straight line. From right of C is also 25. Left of D is 235. So 25 and 235. But we have understood that there is a peak because shear force is changing its sign. All these calculations are required because shear force has changed its sign. If shear force was not changing its sign under UVL, the problem would have become very simple. You can plot it by cubic variation without a peak. But in this case, the bending moment is going to be a cubic variation with a peak coming under this point where shear force is 0. So this peak is coming and this point where shear force is changing its sign. Corresponding to this point, we have calculated the peak value of bending moment as 280.943 kilonewton meter. So you have to show variation from 25 to 235 with a peak, and this is going to be a cubic variation for bending moment. So you can mark it as a cubic variation because you cannot differentiate the parabolic variation and cubic variation while plotting it. So you can specifically mention it as cubic variation and this as parabolic variation. Now from 235 left of V we have bending moment 170, and this part again the shear force is constant, so bending moment variation is going to be linear, straight line variation. So 235 to 170 it should decrease. You can show it by a straight line. And left of E to right of E there is a change from 170 to 130. So that change is at point E because of this coupled, anti-clockwise coupled. So bending moment will decrease from 170 to 130 at that point. Or EF, if you take right of E you have 130, at F you have 0. So 130 to 0, because shear force is constant, you have to plot it by straight line. 130 to 0 is the variation for the section EF, because right of E to F. So 130 to 0 you can show by a straight line. Here you can show 235 to 170. So after getting the variation for the two sections, you can only connect it by a straight line, which will give the variation of bending moment at E due to this couple, that is minus 40 is the variation. Now you got the bending moment curve. So all these variations are linear, except here under UVL you have got a cubic variation with a peak. So all this has become complicated because shear force has come to 0 under this UVL. If the shear force is not changing its sign, then you could have easily plotted without calculating this location and without calculating this peak. You could have continuously plotted increasing this to that right end. Now also there is a point of contraflexure for this beam, that is in the section BC. It's in the section BC. So here you have to locate this point of contraflexure. So this distance you should calculate, and for this section you can write down the bending moment equation and equal to 0. So bending moment equation you can write for this section and equal to 0 to get this point. So let us write the bending moment equation for the section BC. Minus 30x, and this 115 will produce a clockwise moment, and the distance is, this distance is x minus 2. So plus 115 into x minus 2. 115 into this distance, total is x, you have to subtract 2. This is producing a clockwise moment, so plus. So minus 30x plus 115 into x minus 2. That is a bending moment equation, you can equal to 0. So minus 30x plus 115x minus 230 is equal to 0, or this will give 85x is equal to 230, or x is 2.706 meter. So at a distance of 2.706 meter, the bending moment is changing its sign. That is the point of contraflexure. So this distance is 2.706 meter, where bending moment is changing its sign. The point where bending moment changes its sign is known as point of contraflexure. So point of contraflexure is 2.706 meter from left end. So that completes the shear force diagram, bending moment diagram, and we have marked the peak bending moment. Maximum bending moment also you are getting here only, 280.943 kilonewton meter, and maximum shear force is 85 kilonewton. And also we located the point of contraflexure. That's all for today. Thank you for watching.